The 8 a.m. discussion and merge them, or?
Yes, the results of the review of the survey that like most did not mind merging them, so I merged the two discussions at 9 a.m. Yes.
Okay, thank you.
You're welcome. Okay. Any other questions? Okay. So since yesterday was a holiday, you missed another lecture, and so the topic that I'm going to discuss today is one that you probably haven't covered yet in the lectures. So you will most likely rewatch this discussion again after today's lecture. However, I'll try to explain more than I usually do in the discussion so that you can better understand what I'm going to say. And so far we've covered the root locus method and how to use it. And we've covered like some basic design problems where we have a bunch of gains that we want to determine their values, and we use them basically by looking at the root locus and trying to pick a gain that will give us the required transient characteristics and steady state error. But we have not discussed what happens if the root locus does not pass through a region of the complex plane that would give us the required transient requirements. And so today's topic is basically we'd like to design, or we'd like to force the root locus to pass through a specific point in the complex plane that we would like, because it has certain characteristics, and that is done using what we call a lead compensator. And so the first important thing that I want you to understand today, or to get out of today's discussion, is that a lead compensator is used in order to modify the root locus, or to force the root locus to pass through a specific point in the complex plane. And then the second component in our controller that we would like to do today is what we call a lag compensator. So this, let me just write it here quickly. The first part, which is this L, we call it a lead compensator. The second part is a lag compensator. While the lead is required, we designed the lead in order to modify the transient requirements of the system, the lag is used to satisfy the steady state error requirements of the system. And the lead and lag compensator basically have this structure over here. Yeah, it has this structure over here. This is what we call a compensator. The first part, which is this one, this is the lead compensator. It has a 0 and a pole and a gain K. And then the lag compensator is just a 0 and a pole. Okay. And they are characterized by the requirement that for a lead, the 0 is, or the absolute value of the zero is much, much less than the pole. Um, this is for the lead, and for the lag, the absolute value of the zero is bigger than the pole. And we will see now why we do that. Okay. So for the first, or for the question that we have today, we have this transfer function, g of s is equal to 1 over s squared minus 1. And we would like to design a lead lag compensator in order to first stabilize and then achieve the following characteristics. And these characteristics are divided into two categories, or in general, the requirements or the characteristics that we would like to achieve for a control system are defined into, or divided into two categories. The first category is what we call transient requirements, and these concern the transient response of the system. And if you recall from if you recall from the transient requirements of a second order system, the properties that we usually care about in the transient response are the settling time, the peak time, the percent overshoot, and so on. So these are what we call the transient requirements, whereas the probably the only one that we've covered so far about the steady state response, not the transient response, the steady state response is basically the steady state error. So typically what we do is that we design the lead compensator to cover the transient requirements. And then once the lead compensator is done, once we're done designing the lead compensator, we proceed to design the lag compensator. And that's basically what we will do for this problem. So I tried to write this in a, broke it down into several steps and try to highlight exactly what we do in each step so that it's clear. So the first step is basically that we try to translate the transient requirements into dominant pole locations, okay? And so this is quite easy because we know that the settling time, which is approximately equal to 4 divided by zeta times omega n, is less than, or the requirement says that it's less than or equal to 2. So basically, this gives us immediately a requirement on the real part of the roots of gives us a requirement on the real part of the dominant poles, right? So recall that the settling time immediately constrains the real part of the poles. And then the peak time constrains the imaginary part. Again, from this inequality, we can immediately get a constraint on the imaginary part of the dominant pole locations. And then finally, the percent overshoot gives us a requirement over the ratio between the real part and the imaginary part. Any questions? So let me just write here on the side. We know that the dominant pole locations are equal to negative zeta omega n plus or minus omega n square root 1 minus zeta square times I. So this ts, this tp, and then the ratio governs PO. very well. So now these requirements on TS and TP and PO would translate into a region in the complex plane, right? So let me erase this in red first, and then so the requirement on TS. So this is the requirement on TS, right? The dominant poles have to lie to the left of this line. And then TP, the poles have to lie above these two horizontal lines. And then finally, the PO, they have to lie between these two lines. So basically, this defines a region right? This defines this region. And so we would like our region or the poles of our system to lie in this region, okay? The dominant poles. So the second step is basically to check whether or not the uncompensated system, which is the system without the lead or lag compensators, whether or not it passes through this region. If it does, then the problem basically reduces to finding a gain that leads the system to have the dominant poles in this location. If it does not, then we require compensation, or require basically adding or modifying the root locus, which is basically done by using a lag compensator. And so if we look at the root locus of this system, we see that we have a pole at 1. Let me use a different color. We have a pole at 1, and another pole at -1. Okay, and we have no zeros. So basically what happens is that you can see that the segment between -1 and 1 belongs to the root locus. So this segment belongs to the root locus. Maybe I need to increase this a bit. So this segment belongs to the root locus. Now, since these are two poles, they have a breakaway point exactly in the middle. Okay, and what happens is that one of them goes off to plus infinity along the positive imaginary axis, and the other goes to negative infinity along the negative imaginary axis. So we see that the root locus does not pass through the points that we would, or does not pass through the region highlighted in blue here, which means that basically that we need to modify this root locus, which means that basically compensation is needed by basically adding a lead compensator. So in order to proceed, we pick a location for the dominant pole pair. Okay, and that location basically has to lie in this region, right? We can just pick anything in here. To simplify the calculations for the purpose of this discussion, I will pick this point, which we know belongs to the root locus, which we know that it belongs to the desired region, but it's exactly on the boundary. Okay, so a safer option would be to go a safer option would be to go inside the region because remember that the dominant pole locations is an approximation. So by adding and notice here that by adding a lead compensator, we are already adding a zero and a pole. Okay, and so that already um, makes the dominant pole locations approximation a little bit inaccurate. And so what we usually like to do is to be safely within the boundaries of the desired region so that we can actually meet the requirements um, using um, using the design process. However, for simplicity, I'm just going to uh, pick this dominant pool locations, and also to see to show you what happens when we pick something on the boundary. So, anyways, we pick this pole location s equal to -2 plus 2i. The next step in the design process is that we place the zero of the lead compensator directly below the desired location for the dominant poles. And by directly below, I mean that basically the zero will have the same, will be the same as the real part of the desired location of the dominant poles. So because we have s equal to -2, plus or minus 2i, then basically we have z, or in this location, in this expression here, we will have that z1 is equal to 2. Okay, so we basically put z1 equal to 2 here. So now this means that so this means that uh, our compensator GC is basically going to be equal to k times s plus 2 divided by s plus p. And so we have two unknowns left in order to design, or to finish the design process for the lead compensator. And so the next step is basically we would like to find these k and p from the characteristic equation of the closed loop system. And to do that, first we obtain the characteristic equation, right, by closing the loop. So the closed loop transfer function with the lead compensator only is equal to g times gc divided by 1 plus g times gc. And so the characteristic equation is given by this formula. Any questions so far? Okay. The next step is that we try to solve for p, okay, and we solve for p from the phase requirement. Can anyone tell me what we mean by the phase requirement? Does anyone recall? If we look at this equation, any ideas? What do we mean by the phase requirement? Okay, so by the phase requirement, we mean basically this is an equation, right? So if we move the one to the other side, we get this, that this complex number is equal to this complex number, right? And so basically, if this equation is to be satisfied at the desired pole locations, the phase of the left-hand side must be equal to the phase of the right-hand side, correct? And so that's exactly what we do. What we do over here. Let me just go back here. Um, this equation we can just move around the one to the other side to get this, okay? And then which means that the phase of this must be equal to must be equal to negative 180 plus or minus n times 360, right? Because the phase of -1 is negative 180 modulus something times 2 pi. And so if the root locus passes through this pole location, then this equation must be satisfied when we substitute with s equal to -2 plus or minus 2 times I. Okay. And so basically what we do is that we compute the phase of all of these. So this is a phase of a bunch of complex numbers divided by each other, right? So we know that the phase of two numbers divided by each other is the phase, the difference between their phases, right? And that's basically what we have here. So this division translates into difference between phases. And so we also see that the phase of the gain is, or the phase of the gain is basically 0, right? And the phase of, when we put s equal to -2, we get here 0 plus 2i. So the phase of 2i is equal to 90 degrees, minus the phase of this factor here, s plus p, but because we don't know p, for now we will say that this is going to be equal to theta p, and then we will solve for theta p. And then plus, again, we substitute with -2 plus 2i in this factor here, and then we compute the phase of that to get that it's going to be equal to plus 97.1. We move everything and then basically we solve for theta. So theta turns out to be 7.125. So basically the phase of this factor s plus p must be equal to 7.125. Okay, so basically that's exactly what we do. We substitute with s equal to -2 plus 2i into this factor, and then we compute the phase of this factor, right? Which is basically tan inverse of 2 divided by p minus 2. And then we equate that to be equal to 7.125. Which will give us that p minus 2 is equal to 16, so that p is equal to 18. Okay, so now we have solved for s, and we also solved for p. The only thing that remains now is k. So now we have used the phase requirement that the characteristic equation at the desired pole locations must satisfy the phase requirement. The next thing is to satisfy the magnitude requirement, right? Which is to say that the characteristic equation, because it's an equation between two complex numbers, then it also has to satisfy that the gain of the left-hand side must be equal to the gain of the right-hand side. And so to find the last parameter, which is basically the gain, we need to satisfy the gain requirement of the characteristic equation at the desired pole location. So basically what we do is that we substitute with s equal to -2 plus 2i into this expression, and we compute the gain. So because this expression is just we can move everything to the right-hand side to get that k is equal to this. When you substitute, you get that k will be equal to 65. Okay, so so we see that so now we have solved for all the components of our lead compensator. We have the 0. We placed it directly below the required pole locations, and then the pole, we obtained it from solving the characteristic equation by satisfying the phase requirement of the characteristic equation at the desired pole locations. And then finally, the gain, we found it by satisfying the gain requirement of the characteristic equation. The next step is basically that we check that the requirements, or the final step for the lead design process is basically we check that the requirements are met. And we check that basically via simulation. Okay. Also recall that we have we said that the lead will have a pole that is much bigger than the zero, right? And the lag will have a zero that is bigger than the pole, okay? Can anyone tell me or guess why the pole of the lag of the lead compensator is bigger than the zero? Let me go where? Yeah. Any ideas why this is much bigger than the zero? So, okay, so in our design process, where did we place the zero of the lead compensator?
So we placed it by the poles that already exist. So is the reason why we put the new pole far away to the left is because we don't want to interfere with the dominant behavior?
Exactly. Yes, exactly. So if we place the zero, because we place the zero directly below the desired location of the dominant poles, then it makes sense that the pole should lie to the left far enough so that it does not affect the behavior of the dominant poles. That's exactly the reason. Thank you, Mark. In that case, okay. Yeah. So if we do that, if we that's okay. So we were in step 6, right? So we want to check the requirement if the requirements are met. Okay. With this design process, recall that we put the zero exactly below the desired pole locations, right? And with this design process, the root locus is guaranteed to pass, this is important, it's guaranteed to pass through the desired pole locations or that we pick, okay? However, this does not guarantee, okay, that the characteristics are met. Can someone tell me or can someone comment on this, why we're not guaranteed that the characteristics are met? Because we have an additional zero, right? Because we have a zero in the system that, and that zero is typically going to change the transient behavior of the system, right? We said that the pole is going to lie to the left, enough to the left that it's not going to affect, but the zero is or lies exactly below the dominant pole locations, and so it's not negligible. It has the same time constant, and so its effect is non-trivial. And so to do this, typically what we do is that we try to lie or to put the dominant pole locations safely enough within the boundaries of the transit or within the boundaries of the desired pole locations, so that its effective behavior after we add the zero is still not that far from what we would like to achieve. Okay. And so because we picked our dominant pole locations to lie exactly at the boundaries, we should not expect that we get the exact behavior, but we should get something similar. Okay. Yeah, so I left as an exercise for you guys to try to do this design process with s equal to -4 plus 3i, plus or minus 3i. Okay, do this as an exercise and see what happens. If we do the simulation with this, we will see that we'll satisfy the peak time requirement, we'll satisfy the settling time requirement. However, the percent overshoot will be significantly larger than the desired one. And this is typically what happens. The percent overshoot is often the one affected by the zeros, or by the location of a zero, or the additional zero. And so if this happens, typically what we do is that we reiterate the design using different values for the zeros, or for the dominant pole locations. Okay. The next thing is that, so this, like up to step 6, this is the design process for a lead compensator. But recall that we were designing a lead lag compensator, right? So the lead compensator, we use the lead compensator after reiteration to satisfy the transient requirements. Now we would like to design the lag in order to satisfy the steady state requirements. And we would like to do that also without affecting what we already did for the lead compensator, okay? And so the starting step 7, this is the design process for the lag. First, we determine the gain of the lead compensated system, which is basically the system after adding the lead compensator. Okay, and recall that the gain, by the gain of a transfer function, we basically mean the value of that function at s equal to 0. Okay, so that's what the first step is, that we find the gain of the open loop transfer function after adding the lead. Okay. So this is what we call the lead compensated transfer function. Basically, the product between the open loop transfer function and the lead compensator. Okay. Now, if we put s equal to 0 in g of s, we get 1 over, where are we? This is the expression for z. If you put 1 over 0 minus 1, you get -1. And then if you put 0 inside the lead compensator that we found here, you get 2 divided by 18 times 65, right? And so, so the total gain of the system is equal to negative 65 divided by 9. Okay, and this negative is troublesome because the open loop transfer function here seems to reverse the sign of whatever input we give it. Like if we gave, like for instance, if I gave a step input to this system, you see that it's going to change the sign. It's going to flip the sign into a negative sign. Okay, so this sign is quite troublesome. However, it doesn't matter, because when we close the loop, things are fixed when we close the loop, and we will see now why. So now that we have computed the gain of the lead compensated system, the next step is basically to translate the steady state requirements into a gain requirement. Okay. This is what we call KP, which is basically what we would like the open loop, basically what we would like the open loop system to the gain of the open loop system to be. Okay. I'm sorry, the gain of the closed loop system to be. So recall that the steady state error is equal to the limit as s goes to 0 of s times r of s minus e of s, which is basically r of s times minus y of s. Y of s is equal to r of s times t of s. And so this is going to be equal to 1 divided by 1 plus kp compensated. Okay. So this tells us that we would like 1 divided by 1 plus kpc to be less than or equal to 0.1. That's the steady state requirement. When we solve for kp, we basically require either that kp is bigger than or equal to 9, or that kp is less than or equal to -11, right? And so we neglect the -11, obviously, right? And so this is what we require. We'd like the kp to be bigger than or equal to 9 in order to satisfy these steady state requirements. So let's say we pick, again, just for simplicity, let's say we pick that kp to be equal to 65 divided by 9, which is definitely bigger than okay, wait a second. I think I need to do this calculation. 1 second. Yeah, so 2, we'd like this to be 2 times 65 divided by 9, which is approximately 14.4. Okay.
Here, Mahmoud, I don't recognize the final value, the thing in the final value theorem. So the 1 over s minus 1 over s times t of s. Where is that coming from?
Okay, so let me do it like this. So this is E of s, right? Okay, and
oh, so it's just an expression for E of s. So if we did the algebra, we'd get that.
Yeah, exactly. So this is E of s. When you replace E of s, you put R of s minus Y of s, right? And then Y of s is just R of s times T of s, right? And then if you take R of s to the outside, you get so this is R of s. You have here 1 minus T of s, right? And then T of s is just equal to T of s is just equal to G C G divided by 1 plus G C G, right? And then if you subtract, you get, it's going to be equal to 1 divided by 1 plus G C G. Okay, and so the s times 1 over s, this cancels, right? And so you're left with the limit as s goes to 0 of this expression, which is going to be equal to 1 divided by 1 plus the gain of the open loop compensated system after we add the lag. Or that's basically the requirement on the gain of the compensated system.
All right, I see it now. Yeah, it does. Thank you.
Okay, cool. Okay. So as I was saying, we're just going to pick kpc to be equal to 2 times 65. So that more or less, so that just to get just a nice factor here. Let's get so that the 65 divided by 9 cancels, and we get that z divided by p, or we get that the ratio between the uncompensated and compensated system to be equal to 2. Okay, that's basically, and then we set that the ratio between the 0 and the pole of the lag compensator to be equal to this required gain increase, okay, which is going to be equal to 2. Okay, this is the 9th step. We set the ratio of the 0 to the pole of the lag compensator. Let me put this lag compensator. We set it equal to 2. Okay. The next step is basically we'd like to determine the pole and 0 locations. Okay. So this is done by picking the 0 close to the very close to the origin. Okay. And consequently, because the pole is already, we said that it's going to be, the magnitude of the pole is less than the magnitude of the zero for the lag compensator. And if we pick the zero close to the origin, the pole will consequently also be close to the origin. Now, I'm supposed to ask you why this is the case, but because you haven't covered this yet, I'm just going to say here now, and then you probably will understand better when you look at the lecture, when you take the lecture with Professor Marco. If we pick the zero close to the pole and the zero close to the origin, they do not affect, they are not going to affect the root locus of the system. They're not going to affect the root locus of the system. And more importantly, they are not going to affect the design that we made for the for the lead compensator. Okay. And this will be clear when you take the lectures later on. And so finally, if we put the 0 to be equal to 0.1, we get that the pole is just going to be equal to 0.05. And so this completes our design process for the compensated system, right? If you set z equal to 0.1, z2 equal to 0.1, and then p2 is equal to 0.05, we've already designed the leak. So the final compensator is given by this expression here. And then the rest is just closing the loop with that compensator. So this concludes the design process. Let us now go to Matlab to check the transient requirements, or check basically whether or not we met the requirements of the system. Yes. Share. As usual, let me just do the open loop transfer function of the system is given by 1 over s squared minus 1. Okay. And so before we proceed, let's just look at the root locus of that. You see my screen, right? You see my Matlab screen now.
Yeah, we see it.
Okay. So you see that the uncompensated system, you see that the uncompensated system, the root locus of the uncompensated system, just like we already right? So it does not pass through the requirement, the edit requirement. So let's place now the lead that we designed, which was going to be equal to 65 times s plus 2 divided by s plus 18. Okay, and then let's do R locus of G lead times G. Now we see that we see, okay, so let me zoom on this region a little bit. We see clearly that the root locus completely changed, right? And if we zoom on this region, we see that, and also let's put a tip here. We see that the system passes through the points because we placed the 0, right? We placed this is the 0 that we added at s equal to -2, and the root locus, we see that it exactly passes through that point. Okay, like if we increase these resolution a little bit of the 0, we can see that it will clearly pass through the dominant pole locations. Again, however, because of this 0 that we have here and the other pole, we see that the effect, their effect is not going to be negligible. So let's look at, so if we had satisfied the transient requirements for using the lead, we should see that reflected in the closed loop transfer function, right? So let's just compute this feedback G lead times G1, and let's look at the step response of T lead over 10 seconds. Now, if we compute, or if we show the where's the characteristics? So let me comment this and run again. Yep. Settling time, peak response, and steady state. First of all, let's look at if we look at the steady state, we see that the steady state is 16% higher than 1, right? Which means that that the steady state error is 16%, which is higher than what we desire, right? So we require a lag compensator. We have not added the lag compensator so far, but we see that the settling time is 1.81, which is less than the desired value. The peak time is yeah, it's 0.86, which is again also less than the desired value. So we satisfied the settling time and the the peak time. However, we see that the overshoot is actually very large, right? It's 20%. So I'll leave you guys to do the design process for different pool locations and see what happens. Now let's try to add the lag compensator, which we found to be equal to S plus 0.1 divided by S plus 0.05. Then let's, so the purpose of the lag compensator is basically, or let me just call it LL. Okay, this is going to be equal to feedback of G lead times G lag times G and 1. The purpose of the lag compensator is to modify the steady state error, right? So we should expect a little enhancement in this response. 10 seconds and characteristics steady state. So we see that after adding the lead compensator, the lag compensator, we got the required steady state error. So the final value here is going to be 1.07, which is a steady state error of less than 10%, which was required. However, we see a little problem here. The settling time is not. Yeah, whatever. We see that it did not affect that much the response time, and also it did not affect the settling time, but for some reason it's not showing up here. So anyways, this is the design process for a lead lag compensator. I hope that was clear, and it'll be clear enough for you guys when you watch the lecture today. Any questions before we go? All right.
No, I'm good. Thanks, Mahmoud.
Awesome. Thank you guys for your attention and good luck.